let's go back through chapter 4 and review some of the important points. We learned about two new kinds of functions. We learned about exponentials and logarithms. And the exponential function looks like y equals a to the x. And remember, the base a might be 2, or it might be 1/2. Or it might be a special base e. Another special base that we talked about a little bit is base 10. So functions like these are exponentials. And then we also talked about logarithms. And so we said that the log, actually let's write y equals log base a of x is a logarithmic function, and it means a to the y is equal to x. And so when we compare these two, we see that the difference between an exponential and a logarithm is that x and y have switched places. And so that's exactly the definition of an inverse function. And that gave us the important observation that the logarithm is the inverse of an exponential. And we could write some examples. We talked about base 2 logarithm a lot, although base 2 is not really all that special. There are two special bases. There's base 10, also called the common log, and then there's base e, called the natural log. Okay, so we know what an exponential and a logarithm look like. We know that a logarithm is the inverse of an exponential. So let's back up for just a moment and let's talk about an inverse function. And then we'll go and we'll talk about exponentials and logarithms some more. So what is an inverse function? We had a definition of an inverse which said that g of x is the inverse of f of x if g circle f of x is equal to x and f circle g of x is equal to x. And remember that f of x, in order to have an inverse, has to be 1-to-1, where f of x is 1-to-1. And so we talked about definition for 1-to-1, which says for each output there's exactly one input. And then we talked about a corresponding horizontal line test. And then we also talked about function, which the definition of a function is for each input there's exactly one output, and that generates a vertical line test. And we found an inverse 3 different ways. We found an inverse 3 different ways. We found an inverse from a table, and from a graph, and from a formula or an equation or you might say algebraically. And so we can recognize an inverse function in each of these three ways. We can also recognize a function, whether a function is one-to-one or not, using either the definition or the horizontal line test. And remember, the classic example of a function that's not one-to-one is a quadratic, is y equals x squared, for instance. The parabola is not one-to-one. Okay, let's go on and let's talk about what we did with exponential and logarithmic functions. And basically it falls into three categories. We looked at the graphs of basic functions, and then we looked at transformations of those basic functions. We also solved equations with exponentials and logarithms, and then we looked at application problems. And so let's go through those one at a time and give a few examples. So what are the basic functions we're talking about? We have three of them. We have y equals a to the x, where the base a is greater than 1, and we call that exponential growth. We also have y equals a to the x, where a is between 0 and 1, and we call that exponential decay. Notice that for exponential growth, the function is increasing, and for exponential decay, the function is decreasing. And then there's one more that we want to mention. It's y equals log base a of x. And remember, that's just, with logarithms, we're only concerned when the base a is greater than 1. And so then the graph of the logarithm function would be the inverse of the graph of y equals a to the x, this first graph. And graphically speaking, what does the inverse look like? It looks like a reflection over the line y equals x. So we get to this picture right here with a vertical asymptote at x equals 0. Okay, and then we could talk about transformations for just a minute. For transformations, if we have y equals the common log of x plus 3, then what is that transformation? That's a shift left 3, and you could draw that. And then you could compare that with this function. This one is maybe just a little bit confusing because you might not be sure what you're taking the log of. Are you taking the log of x or x plus 3? And the convention is to understand when we have this that we're only taking the log of x. So the plus 3 is outside of the basic function. The logarithm happens first and then the plus 3 afterward. So this would be a shift up 3. So the second one is shift up 3. The first one is a shift left 3. We also did reflections of logarithms and exponentials. And we talked about how the asymptote can move when you shift an exponential or a logarithm. We did not talk about stretches or compressions of exponentials or logarithms, and so they would not be on the exam. Okay, so that's the graphing. The next thing we want to talk about is solving equations. And so let's just write out a couple examples here. We have, first of all, we have 2 to the x equals 8 to the x plus 5. And do you remember the first step for this problem? In this problem, we saw that the bases can be written with the same base, or that the two exponentials can be written with the same base. And so the first step was to do that, was to write this 8 as 2 cubed. And then when the bases are the same, we can just set the exponents equal to each other, and we can go on from there. I'll just put a dot, dot, dot. I won't finish the problem. Another possibility was 2 to the x equals 7 to the x plus 5. And in this case, we can't use the same base to write both exponentials, and so we need a different technique. And so remember what we did? We took the log of both sides, and then that allowed us to use a property of logs to bring the exponent down in front and then go on from there. Number 2 there is a tricky problem. It's often on the exam, and it's difficult a lot of times for students. So be sure to look back at a problem like that in your homework in section 4.5. Okay, let's write a couple more examples. Another equation that we looked at was something like log of x is equal to 3. And we said there's two ways to do this. We said we could just go ahead and write the log as an exponential. And we could do that immediately. The base 10 raised to the third power is equal to x. Here, let's write that in green to be consistent. The base 10 to the third power is equal to x. And so we've already solved the problem. X is 1,000. And then we also said that we could just put a base 10 underneath both sides of the equation, and then the 10 and the common log cancel, and that just leaves us with x on one side and 10 to the third on the other side. Okay, and then the fourth example that I want to show you is log of x plus the log of x plus 5 equals 3. Okay, so log of x plus log of x plus 5 equals 3. And so do you remember the first step that time? We had to use a property of logs to rewrite the left side as a single log. Right, the property says multiply the two arguments together. The brackets aren't necessary, but it's a nice way to emphasize that the x and the x plus 5 are together inside the argument of the logarithm. And then from there, you can proceed just like before, just like in the previous example, where we just put a base 10 underneath both sides, or just write the equation as an exponential directly. Okay. The other thing that I wanted to talk about was solving application problems. You should memorize these formulas. You will not be provided the formulas on the exam. So there's a formula for compound interest, which is A equals P times 1 plus R over N to the NT. And A equals PE to the RT. And then for exponential growth and decay, that's really the same formula as the continuously compounded interest. We just use different letters to represent the initial amount and the future value, and K is a growth rate if it's positive, or it could be a decay rate if it's negative, if K is a negative value. Okay, so those three formulas you need to know. pH was a formula that we learned that involves a logarithm. We said pH is equal to the negative common log of the hydronium ion concentration. You don't need to memorize this formula for the exam. This formula is given on the exam, just the pH formula. Okay, so you should look back at examples of each of these. And then last, I want to mention the change of base formula. You should know that. It's in section 4.4. I don't think I need to write it down here, but you should definitely look at it. There are 3 big properties of logs, and then there are 2 more properties that are, 5 total officially in your notes for section 4.3. And then the properties of exponents is prior knowledge that we tried to review as needed in section 4.2 and throughout the chapter. So definitely want to look back at the properties of exponents that you saw in the videos and that you saw used in the examples in the textbook and in your homework. Okay, before we stop, I'd like to go back up. I'd like to go back to the top. I'd like to look down our list again, and mostly I'd like to point out which section the material is in, so that if there's something in particular you have a question about, you'll know where to look for it. And so once again, from the top, we talked about exponential functions and logarithmic functions, and the exponentials were in section 4.2, and the introduction to the logarithms were in section 4.3. And then we had this big idea here: the log is the inverse of the exponential. That's in section 4.3. And we talked about the base 10 and the base E in section 4.4. And then let's go on and let's look at this inverse function. Inverses was the first thing that we learned about. Inverses were in section 4.1. Okay, what did we do with exponential and logarithmic functions? We saw their graphs. So this graph is these first 2 graphs, the graphs of the exponentials, are in section 4.2, and the graph of the log is in section 4.3, and then the transformations are in section 4.2 and 4.3. And then when we solved equations, this first example we solved in section 4.2, but then the harder one, the harder equation in example 2, we didn't solve that until section 4.5. And similarly over here, example 3 was in section 4.3. It was an easier example of a logarithm, of an equation with logarithm in it. And then example 4 is an example of a harder equation with logarithm in it. It was in section 4.5. Okay, and let's keep going. Let's look at the compound interest. Compound interest was in section 4.2. Continuously compounded interest was in section 4.2. exponential growth and decay was section 4.6. And really, this formula is the only thing in section 4.6. And or applications of this formula is the theme in section 4.6. The pH problem was in section 4.4, along with the change of base formula. Okay, it's a lot. It's a lot. Think about exponentials and logarithms, and good luck on the exam.